as part of the that's thrown me off a little, hasn't it? I'm a researcher at Leicester, working as part of the UK's NICER project. This is all to do with the circular economy. And in particular, I work in the Met for Tech division, which is looking at technology metals, issues surrounding their supply, and things like that. So that's what I'm going to be talking to you today about: critical technology metals and mining in the 21st century. So what I'd like to ask first is, what are your perceptions of mining? I'm happy for anyone in the room to shout out anything they think about mining. Digging holes in the ground. What a fantastic, fantastic thing. Yeah, this is probably, you have a feeling this is what mining is like. It's a really big hole in the ground. There's some diggers over here that look tiny, but actually are twice the size of your house, that sort of thing. But unfortunately, if you read the BBC News or read The Guardian or The Independent or basically any newspaper in the UK, you might also have rather a bad opinion of mining. So this was Hungary in 2015. A tailings dam breached and it spilled 30 kilometers of toxic waste out across the countryside. Unfortunately, I think 6 people died. And then this is 2019. This is Minas Gerais in Brazil. Again, another tailings dam breach. This one contaminated land and water supplies 300 kilometers downstream of where the breach occurred. And unfortunately, over 200 people died in this particular disaster. Or it might be one of, something like this. This was just 2020 this occurred. A mining company, while they were exploring for iron, blew up a culturally significant location for the Aboriginal Australians. And the bad news keeps going. Conflict minerals. This might be what you think of when you think about mining. The trading conflict minerals have been going on for the best part of 100 years now. And it's almost as if the mining companies knew I was giving this talk, because 2 weeks ago, they lost a radioactive capsule of cesium in Australia. So you might just think they're just careless. Fortunately, they found it eventually. And it's a real shame. And I'm not trying to say that, none of these things are awful, because they are terrible. And these represent some of the biggest challenges facing mining companies and mining in the 21st century. But there's another side to it that I think is sometimes forgotten. And that is all the amazing benefits it actually brings our everyday lives, because we live in a world of metal. All of the things around us are made of metal. Steel to make our buildings where we live and work. Aluminium for our cars, and other metals for manufacturing. They give us all these conveniences. Copper carries electricity into our homes, gives us hot water on tap. Couldn't live without it, could we? And increasingly nowadays, we have all these little gadgets around our homes, and these are all full of rare and unusual metals that enable them to work. So we're surrounded by metal all the time. And increasingly nowadays, you also see articles like this: the perfect storm increasing the cost of crucial metals. Or, do we have enough lithium to power the world? Rare earths. You hear a lot about rare earths, particularly to do with China. And this was, again, a few weeks ago, huge rare earth discovery in Sweden. They're talking about this being game-changing for Europe, because there's a new narrative, this critical minerals narrative. And this has been going on for a while. The government is very keen on it. Net zero. This is our green technology, the transition from oil to greener technologies. This is just the UK's demand for a few of the metals. So if we're going to meet these net zero targets, 10 years of global neodymium and dysprosium, 10 years of global production, 2 years of the annual cobalt production, 1 year of global lithium production. It's a lot. That's a lot of metal. And the problem is, it's not just us. Every country wants to do it. And suddenly our interests in the UK are crowded out a little bit. Because metal, it is the new oil. This is a phrase you might see fairly frequently if you peruse the trade papers like I do, when I'm meant to be working. The new oil, because a future that looks like this, green power, no emissions, is going to involve a lot more of this. So speaking of this, what really is mining? Well, when you strip it all back and you take away, oh my God, this big hole in the ground, mining looks something like this, rather humble diagram. We take a concentration of metal in the ground, we dig it out, we crush it up, increase the concentration of our target metals, process called beneficiation. You get a concentrate, you send it to your refiner, you get your metal out at the end. And there's a few other bits. There's some tailings, bit of waste going on, fairly simple, but this is, fairly abstract. What does it really look like? It's one of these big number things that humans are bad at. If I say a ton of rock, can't really picture a ton of rock, can you? Or can you? So what if I'm a platinum miner? If I want to mine some platinum, well, first I need my ore. This is from the Plant Reef in South Africa. Obviously, this is not a ton. I'm not Superman, but I can show you what a ton of that rock would look like. In fact, I'm going to show you what 2 tons of that rock looks like because it makes the maths more convenient. Sorry for people at home who can't quite see what I'm doing. There is a little demonstration aspect to this. Oh, I'm keeping going. Think we're there yet? No, not quite. So I need some more moving boxes. Can you tell I moved house recently? So that is our volume of 2 tons of this ore. Sorry to my wife and George, hiding around the corner, can no longer see. I will take this down a little bit. But that's our 2 tons. We're going to take that, we're going to grind it up. But there's an important number here. It's only 2 grams per ton. So if I have 2 tons, there's only 4 grams of platinum in that. So when I get it out the end, anyone know what 4 grams of platinum looks like? Roughly? Very small. In fact, that is 4 grams of platinum. For anyone at home who will not be able to see this, this is my wife's wedding ring, very kindly lent to me. And I'm glad the boxes are there because I can feel the glare coming from that direction. That's all we get. From that massive pile of rock, that is all we get. We throw all of that away. It goes to a waste tip somewhere. And it's not just waste that's involved in this, there are other costs. So to get that, 1.6 tons of water has been used. And we've emitted 134 kilograms of CO2, all for that tiny wedding ring. And I would guess there are some other people in this room who have wedding rings or other jewelry on and might be thinking, oh, I'm glad I don't have a platinum one, I have a gold one. Gold's worse. So that's the kind of costs we're talking about when we're talking about mining. I want you to keep those in mind as we go forward. I'm just going to bring these down so the nice people in the corner can see a bit better. So over the last 300 years, the amount of metal we've used has changed drastically. We've gone from a situation back in 1700 where we used a handful of metals, but they were important to everyday life. As technology developed, we used more and more. And it's this technological development that drives it because we use different elements to get different effects. When we started building steam engines, suddenly we needed stronger metals. So we put tungsten in our steel to make it really resistant. Automobiles, well, suddenly we needed catalytic converters. So platinum became essential, and copper wiring and electrification. And we get to today, we have over 60 metals that we probably all use every day without even realizing it. And they're essential for our way of life to continue. And this diversification in the amount of metals that we use, it's occurred at the same time as the physical amount of metal has increased drastically. So this is the global production of some base metals from 1900 to 2017. As you can see, we trundled along fairly, some modest growth during this point, and then about 1960, suddenly we start using more and more and more. The blue line is aluminium. You can kind of guess when we started driving lots of cars because suddenly we used a lot of aluminium. Copper is the red line. And the main drivers of this, well, at this period, the post-war boom, mass industrialization in the West, and then going into the economic miracles in Asia in the late 60s and 70s. Slows down for a bit. And then since about 1998, this growth has been in part driven by this diversification of more gadgets in our homes, more metals in our lives. But also, this is China and this is India, as they have urbanized, industrialized, trying to raise the standard of living for their people. And what about future demand? Well, we were talking about those net zero targets. What are we going to need? Well, this is the projected copper demand. Today we buy in about 28 million tons of copper every year. You can see that number is going to go up and up and up and up and up and up and up. So by 2100, 90 million tons of copper. So year-on-year increase, and fairly prodigious increase, especially for the next few years as we try and build essentially entire new infrastructure. Because look at those green technologies. So here's a few of them. They use a lot of metal. Up the top there, we have our electric cars, and we have copper, we have nickel, we have manganese. The conventional car doesn't actually use that much by comparison, but also our power generation, offshore wind, a vital thing in the UK's net zero plans, a massive amount of copper, another huge amount of zinc, talking 16,000 odd kilograms. This isn't even thinking about the steel and the aluminium that goes into building these things. If I was to do that, it goes off to the other side of the room somewhere. So there were lots of different metals on there, and that's what these technology metals are. They're these kind of lesser used ones, but they're in everything, all the circuit boards in the computers, all of your smart devices, the green technology, so making magnets and things like that. And they're not used in huge amounts in any particular application. We don't even produce very large amounts of them, but they are vitally important to us. If we look at an average smartphone, I for once don't actually have a smartphone on me. This is an incredibly rare occurrence. You people here probably do have them. I can see a man with a camera. There's definitely a few of these elements in that camera. If we just look at a simple phone, your display is full of rare earths. Your electronics, strange minerals like gallium and tantalum, those are in your semiconductors and things like that. Casing, well, that's kind of traditional metals, that's fine. The battery though, lithium, cobalt and nickel. And then again, in your touch screen and your displays, you have more rare earths and indium. It's a strange metal, indium. Well, every touch screen, that's what lets it be a touch screen, because it's highly conductive in very thin layers. Another power generation, we haven't talked about solar panels yet. Probably won't use them that much in the UK because, well, it rains a lot here, doesn't it? But, there are places where these are going to be really important, and they use tellurium, molybdenum, beryllium, germanium, gallium. They get strange elements. So where do we get those things from? Because, I've heard of a copper mine, I've heard of a zinc mine, iron mines. I've never heard of an indium mine or a gallium mine, because they don't exist. We get them from other deposits, because other deposits are enriched in more than just the thing that we mine mainly out of them. If we take these ones in the middle here, the upper middle diagram, this is a porphyry copper enrichment pattern. So this is the enrichment relative to the crust of these particular deposits. And this one in the center, it's a copper deposit. So if you look in the, about the 2 o'clock position, it's quite enriched in copper. It's also quite enriched in gold, which, yeah, gold is quite a common product from these deposits. It's worth a lot of money, it's worth getting. But then you look and there's other things. There's tellurium and selenium. There's tin, tungsten, rhenium, molybdenum. A whole range of elements are enriched. And this is true for all of these deposits. If you look, there's, lead zinc deposits. Yeah, they're enriched in lead and zinc, but they're also enriched in a whole bunch of other things like bismuth and stuff. And it's because those geochemical processes that concentrate metals into a deposit, where it doesn't just act on one metal, it acts on a whole suite of them. So your average ore deposit is highly enriched in many elements. Just we don't target all of them. So in our mining paradigm that we had earlier, copper, this is a new one. Should we play our game again? Yeah. We've got 2 tons of copper ore. Copper's a bit richer though, about 0.5%. So how much copper are we going to get out from our big pile? Ballpark estimate, anyone? 2 tons of ore, Oh, but I see he's undersold me. He's made it seem like actually it's really good now. No, you get about 10 kilograms out of that, which is about that much, that small box. So again, very wasteful process. And when you think about how much copper is in the world, wow, that's a lot of waste, isn't it? Think about just your house, how much copper is in your house. Anyway, if we have copper, well, there are other things in there, as I showed you. So yeah, we can also get some gold out. Gold would also be called a product in this scenario because it has a similar, overall worth, even though there's a lot less of it to the copper. So we call it a product. Sometimes those porphyry deposits might have a good concentration of molybdenum. This is worth a bit less, but it probably can still pay for its own things. We call that a co-product. So the co-products up there. And then there are those other things. Those are things that are in there in concentrations that can be economic, but aren't really worth a lot, but are vitally important. Those are our byproducts. So what happens with these is it goes through this, and the kind of byproducts, they hitch their way along with the main metal. And then it's only when you get to this point at the end that they're really paid attention to. People down that end don't care about them. Over here, the refiners, though, they'll take them out and sell them for a profit. So because they produce as a byproduct of one other thing, it makes them dependent on the production of that thing. So our tellurium, selenium, rhenium, even our molybdenum to an extent, they're dependent on the production of copper. Because at this part that's highlighted in red, the front end of it, where the mining companies are, they're mining copper. They're not mining anything else. They're mining copper, a bit of gold, not paying attention to the rest of it. So suddenly the production of these other metals becomes dependent on how much copper is being produced. And this is what's known as companionality. So here we have a work by a man called Nassar in 2015. He published this, and this wheel illustrates companionality among byproduct elements. So in the center, we have our main products, things we're familiar with: copper, zinc, gold, that sort of thing. And radiating around them, you have all of these other elements labeled. And the closer it is to the center, the more of that element's production is as a result of that material in the middle. So copper, which we were talking about, I've already mentioned tellurium and selenium. Well, tellurium and selenium only come from copper deposits. So it's through the refining of copper that we get all of our tellurium and selenium. There are other elements where this is true. Indium comes from zinc refining. And the whole range of the platinum group elements, unsurprisingly, come from platinum mines. Gold is suspiciously absent of any production other than gold, because gold miners care about one thing. But this dependency is a real problem. Because what is the distribution of deposits? Because if it's reliant on one thing, then that means the distribution of that one controls where it's coming from. So using our example of copper, where we had selenium and tellurium being completely dependent on copper. Where are the copper deposits? Well, they're spread out around our subduction zones around the world. So we have, the active ones in the Andes, going up through Central America and into North America. Have the other side of the Pacific, where you have Indonesia and the Philippines, where you have porphyry copper deposits. And then you have a few of the paleo arcs. So through the old Tethys Ocean, you get some deposits. It's really these modern ones that are the really important ones. And if we look at copper production, well, yeah, it's dominated by those places. Chile is the world's largest copper producer, followed by Peru, and it's the USA and Mexico. Yeah, it's not surprising. This is where the deposits are. It's not an even distribution across the world. And this is common for a lot of things, geological deposits, they're only in with some places. If we look down that list of some important minerals that we have, I see a lot of countries that we might not consider friends there, or we might have some worries about trading with them. There's one in green up there that is not very popular anywhere in the world at the moment. China has the dominant supply of graphite and the rare earth minerals at the moment. Australia, we are friendly with Australia, but they have a lot of lithium, that's good. And South Africa for the platinum deposits, they're very dominant. So the supply of those elements, but also those byproduct elements that come from these deposits, is dominated by those countries as a result. Oh, sorry, that's in there by accident. So yeah, so what about the other half of the equation though? So we had, that control of where a geological deposit is, but then we had this bit, where the material is actually realized in our refineries. Because refineries aren't evenly distributed around the world either. There aren't many smelting or refining operations in the UK, as far as I'm aware. If anyone correct me on that, I'd love to know where they are. In fact, there aren't many in Europe. There's one in Belgium, there's one in Sweden, there's a small one in Germany. Yeah, there's not much. Where are most of them? We're looking at global copper production. So on the left, we have our mined copper again, but on the right, we have our refined copper. So these are the guys that are mining it, but these is where it's being refined and ultimately sold. So we have our geographical control on the distribution of minerals, but then we have this other control, which is entirely of our creation. So if we look at that, China mines 36% of the world, refines 36% of the world's copper, despite mining only 8.5% of it. And countries you would think would be, big players in the copper world, suddenly are less significant. Chile, the world's biggest copper miner, it only refines 5.5% of the world's copper. And then there are countries that are absent from this side that suddenly appear when we look at who's actually producing copper. Japan is one of the world's biggest copper refiners and sells it and uses it for their industry. Japan has no native copper deposits. Belgium is on here. Belgium. There are no copper deposits in Belgium. And what this means is that you have this control. So these countries over here, they're able to do this because concentrates are freely traded. So given the last diagram, this one's pretty unsurprising. Chile's the biggest seller of copper concentrate in the world, and China's the biggest buyer of copper concentrate. So concentrates are traded freely. It means that anyone can conceivably produce it, but most of those refineries are actually in Asia, particularly in China. And that gives China and other countries like that who have the refineries control on that supply of these critical elements. So if we look at the refined selenium and tellurium, who's the dominant player? Well, it's who's refining the most copper. It's China. China is 34% of refined selenium, 60% of refined tellurium. Japan, no native deposits, is very significant for tellurium because they use it in the electronics industry. They've secured their supply by buying from Chile to keep their industries running. I think our government could probably learn a fair bit from Japan's trade policy, maybe not some of their other things. They're also one of the nations with big stagnation of economics at the moment. So there's a concern about the supply of these metals because they're so important for our everyday lives, for our manufacturing sector, and yet we don't have control over them, particularly in the UK. We don't have mines, we don't really have any deposits, we don't have refineries, we just have to buy on the open market. And what if one of those countries we're not friendly with that controls so much of the supply just doesn't want to sell to us anymore, wants to keep it back, use it to build up their own green industries? It's conceivable. And China's the biggest concern because it has become the world's foundry. These are some of those critical minerals that we were talking about, and you can see the dominant factor in all of them is China. China has spent years building up its refining capacity because no one else wanted to do it. It's a dirty business. As a result, that's why these metals are considered critical. This is the UK's critical metals list from a few years ago. The UK, oddly, doesn't really consider many of the major products critical. Seems to be fairly confident in that can just trade to get them. But all of those byproducts and those high technology metals, those are all up there. Rare earths, very important. Tellurium for solar panels, apparently very important. Yeah. And this is, it's a global thing. But countries all over the globe are doing these. And you end up with this general critical minerals picture where you have, your rare earths and your technology metals that are purely produced as byproducts up there. Down here is your main products. Japan, like I mentioned earlier, they actually consider copper a critical mineral. They're the only country in the world to do it. It's because what I was saying earlier, where they refine it and get their critical technology metals from it. So they acknowledge that one of those carrier metals is actually really important. I remember that projected copper demand going up and up and up and up. Well, we need some of that. And it's looking increasingly difficult. We might get it. You know, it's the question of, are we going to run out? Are we going to run out globally and not being able to find enough? Or is, you know, a country like us going to run out because we just can't trade for enough? And while I was making this talk, I found this quote that seemed rather apt for our modern age. The age of electricity and of copper will be short. At the intense rate of production that must come, the copper supply of the world will last hardly a score of years. Our civilization based on electrical power will dwindle and die. It's rather fatalistic. It's not a cheery outlook. But I was very surprised when I looked at what year it was made in. This was actually from 1924. So this was from the first wave of electrification, where there was a sudden demand for this metal that hadn't really been used a huge amount. And people thought they were going to run out. The truth is, despite what most of the articles say, the world isn't going to run out of copper. It's not going to run out of basically any metal. There are lots of metals out there. It's just, can supply keep up? Because we don't necessarily target all the metals we should. And also there's a big delay. So if you don't find enough, you don't open enough mines, supply might drop and it might be hard to get, but we're never actually going to run out. And, you know, we have other tactics. We have recycling. It's very popular. Lots of articles on the BBC. You get the Royal Mint getting very excited about getting gold out of phones. You have this article in the front of Middle that certainly made all the mining geologists in the department a bit worried for a while. Mine e-waste, not the earth, say scientists. If we could do that, I'd be in favor of it. But there is an issue with recycling. And it's that there's a lifetime of these things. So if we need an increasing amount every year, you know, if the next year we need twice as much copper as we needed the year before, there's not enough for you to recycle. And if you look at this, this is some modeling of tellurium supply based on recycling of solar panels, and it demonstrates the next point of, you know, the base case here is just was it a 0.1% recycling rate, and these ones are if you increase it. And there's still a supply gap, and that supply gap is because of a lack of primary production. You can recycle as much as you want, but if you put a solar panel on your house, you expect it to last for 20 to 30 years. So if someone needs some tellurium the next year, you can't recycle your solar panel to build it, can you? So you need to keep putting into it before recycling becomes more effective. So what's the answer? We need more mines. Yes, mining. We're back to this. So we need more mines. But as we discussed earlier, there are some pretty significant issues with mining. There's a footprint, waste. So that's those big tailings piles. Water. It's a desalination plant in Chile, but it's not providing water for people, it's providing water for mines. And CO2. I mentioned CO2 earlier. It's a big processing plant in a mine. They produce a lot of CO2 and they use a lot of electricity. So what a waste. We had our copper example earlier. 99% of all that material is discarded from our copper because it's only 0.5%. So it means that if you have a hole like this, which everyone was very happy to see earlier, you've taken that out, you've taken your copper out, but all of that material is waste. Other than that 0.5% that was copper. So that hole, basically you throw everything away. And how big is that hole in the ground? Well, that's it from above. I apologize for the contrast. It's much clearer on my screen. So this is Escondida, one of the world's largest copper mines. Chances are you own something that has copper in it from Escondida. It's about 2 kilometers wide, about 5 to 6 kilometers long, depending on where you measure it. 650 meters deep. It's a very big hole. There it is. It's about that big. But once you take into account all the waste and the processing, the footprint of that mine suddenly gets a lot bigger. And you all know what I'm going to do next, because it's what every person who does one of these talks does. I'm going to drop it on Leicester. So there we go. One copper mine, one of several thousand copper mines in the world. You know, this is a particularly big one. The pit essentially covers up, you know, well, we lose Foss Park. No great loss. Yeah, what a shame. Unfortunately, I think we're sitting underneath about 200 meters high worth of tailings right now. House prices in Great Britain probably aren't doing great, but they're better than most other places in Leicester, which basically doesn't exist at this point. So we have a huge issue of waste. If we need to mine lots more copper, we need somewhere for all this waste to go. I think you can agree Leicestershire is not the place for it, but it needs to go somewhere. What about water? I mentioned water. Water resources around the world are incredibly vulnerable, and in a warming world, they're getting more vulnerable. So this map, all the little dots here, the blue ones are porphyry copper deposits. The pinky purple ones are porphyry copper gold deposits. And there's some dark gray ones. These are lead zinc deposits. As you see, it's where we expected them, along Chile and into the US, as well as some out in China. The redder the image, the more water stressed that location is. And if it's gray or black, that means it's arid. There's no water. As you can see, most of our mines are actually in areas where water is in very short supply. That's despite us needing a huge amount of water to do mining. And it's those energy transition metals that are actually in the most danger when it comes to water. Copper and lithium, the most at risk when it comes to water security. And it's not just water security for the mines. As I said earlier, they now compete with water that needs to be available for people. Chile is having a lot of problems at the moment with mining taking up too much of the water. So there are actually shortages in the city. So the people are suffering so that people all around the world can have copper. And CO2, diesel, electricity, and acid. Unfortunately, at every point of this process, we use one of those, or we produce one of those. So when we're digging out the ground, all of our machines are powered by diesel. When we're crushing everything up, that's all electric, or we run on diesel. Last year, 3% of the world's produced electricity was used to crush rock. 3% of all the world's electricity. And unfortunately, most of that is still produced by burning fossil fuels. So that's a huge CO2 emitter. And when we get down to this refining stage, a lot of refining processes use acids. And these acids, once they're used for their main purpose, have to be neutralized. And that's unfortunately done most of the time by pouring them onto limestone. As you can imagine, that emits a huge amount of CO2. Also takes tons of electricity as well. So every point we're having problems with CO2 emissions. And it depends on the commodity, but some of them are really bad. And unfortunately, it's, the ones we need for our energy transition are actually worse. So copper here, it looks relatively good compared to some of these other things. Lithium carbonate's okay. Nickel for our batteries, it's starting to get a bit bad in terms of the CO2 emissions. Neodymium oxide, I'm really glad we don't need a lot of it. It's a very small component in magnets because it is by far the worst, almost 80 kilograms per ton of metal equivalent. 80 kilograms of CO2, so that's really bad. And some of you might be going, why are we doing all this green stuff? If it's going to cause so much damage doing it, should we be doing this? Well, looking at the metals contained in an electric vehicle versus an internal combustion vehicle, that's ICE, internal combustion engine. If we were to ignore steel, then there is way more metals in the EV. Fortunately, the internal combustion steel is heavy. And in terms of rock mines, though, because the EV things are much rarer, much lower concentration metals, we have to mine a huge amount more rock to get an electric vehicle. And we need to make the estimate is about 2 billion electric vehicles to replace the current cars and buses and things like that. It's like, is it worth it? Is this really worth it? The damage it's going to cause, the huge amount of waste, the water resources, the CO2. Yes, it really is worth it. Here we have some modeling that was done, and it shows the CO2 impact over the lifetime of a vehicle. So on the left, we have our two electric vehicles, and on the far right, on this one here, the ICE one is our internal combustion engine. And while actually manufacturing these vehicles is far more intensive, the fuel that runs it is the problem, the main thing with cars. So over its lifetime, your average internal combustion engine produces far more CO2 than is produced by manufacturing your electric vehicle. There is a caveat. Some of you may have noticed two rather large error bars on that diagram. because ultimately electric vehicles, the final number, it depends on where you get your electricity from. If you are charging it with electricity made in a coal power plant, it is just as bad as an internal combustion engine. If you're charging it with power from a solar panel or a wind turbine, suddenly it becomes a whole lot better, and it can actually get much better. So we need more better mines then, don't we? You know, if we need to mine more and we're going to have to mine more, we need better mines. And how do we do that? Well, we need to be more materially efficient. So in our scenario with copper, we can't just get copper. Oh, my animation has gone in a strange order. So I'll just get these all out. We can't just get copper. And gold, well, gold's valuable, but it's useless. So let's forget the gold. You can get it if you want. It pays for everything else. We need to be materially efficient. We need to extract as much as we can from every ton of ore. Because if we're going to be producing, you know, basically a ton of ore for a ton of waste for every ton of ore mined, we need to make it really worth it. We need to extract all the metals that we can. And we need to do something about that CO2 and that diesel output. And you know, that could be as simple as just changing the way we power our mines. If we shift from, you know, fuel, diesel, natural gas, or to low carbon electricity or renewables, we can drop that amount of CO2 per kilogram of refined copper massively, of any metal. You know, if we go full electrification, we can get that right down. And it's never going to be zero. There's always going to be a bit of fuel involved. We're probably always going to have to burn a bit of diesel or, you know, something like that in order to make these machines work. But we need to get it as low as we can, so that the benefit of using these metals to make renewable technologies that are clean, we get the maximum benefit from it. And that's, you know, what we're trying to do at Leicester in part of the Met for Tech program. So what we do here is we look at our geological resources. We do analysis and modeling on the resources in the ground, because while we know the byproducts are in those things, the companies don't explore for them. So we don't actually know how much of it there is. We're pretty sure there's enough, but we don't know exactly how much. We don't know where it is. So we're trying to do stuff to work that out. We're using advanced machines and workflows to actually look at the ore, to look at the concentrates and see, other than just, you know, our copper or our iron, what are the other metals in there and what can we do to get them back? And we're developing new refining technologies. Deep eutectic solvents. My colleague Gowan Jenkins did a talk a few years ago, as Tom said. And we're looking at using these to extract metals in a more efficient way. Sorry, it seems to have frozen. Oh. Sorry about that. So when I'm talking about, you know, modeling resources, what am I doing? This is part of what I do with my day-to-day job. I use machine learning to try and take data sets and use them to infer what is in unknown deposits. And don't worry, I'm not going to bring up a screen full of code and start chatting to you about that. That would be an incredibly dry way to end the talk. So it's just a general workflow. But the thing is, we've done a bit of this. And remember that metal on the UK list, tellurium? We've spoken about it a few times. It's one of our most significant ones, according to the BGS. We've been trying to predict tellurium grades in not just copper deposits, but other deposits. And we've been able to show that actually, a bit on the far right is the important. This is, you know, just what went in, what came out. In your average copper deposit, there is actually quite a lot of tellurium. In fact, there's so much that in just these 6 deposits that I looked at, there's 13 times estimated global production. That's a lot of solar panels. So that's what I was saying earlier. These metals are there. We're not quite sure where they are. This suggests that, you know, if we optimize production from just a few deposits, we'd be able to provide all the metal we need for net zero transition. And the really interesting thing is, 2 of these deposits, the bottom 2, are not actually porphyry copper deposits. These are orogenic gold deposits in Africa. And earlier I said, you know, gold deposits don't produce any significant byproducts. They just focus on the gold. This suggests that maybe they could produce significant byproducts. it would actually make mining that gold a bit more worth it, other than just monetary gain. The second part of what we're doing, looking at the flows of metals through different ores. So this is a project that's currently being undertaken by one of our PhD students, Lara Tretton. She's looking at the Björkdal gold mine in Sweden. She's taken their ores and she's identifying these new interesting minerals that are in them. So they just mine gold at the moment, but she already has identified that there is a potential tungsten resource in the form of scheelite in these things. This is a much loved picture in our little group. It's our Barney the dinosaur mineral because of the neon color scheme. She also found other things like bismuth telluride, all critical minerals that are needed for transition, and they're all there, but they've never been exploited properly before. So she hopes to track them, and this is their flow sheet that they have at the plant, and she's tracking them through the different parts of it and looking for where do you get losses, where does that end up, and how can we then recover those metals. And the final part of it, the deep eutectic solvents. We're really excited about deep eutectic solvent in Leicester, in part because they were invented in Leicester by Professor Andy Abbott. So we're all very, very proud about that. Also because they have a huge potential. So they're combinations of halide and metal salts and hydrogen bond donors. The point about that is that they have very high chloride contents, and they're very good at dissolving metals and metal-bearing minerals as a result. They're generally environmentally friendly. The things that make them are fairly benign. Gowan has a famed presentation that would now show you a picture of a chicken, because one of the key ingredients is chicken feed. But one of the key things in terms of what I've been talking about the energy involved, is they are effective even at very low temperatures. So whereas a traditional refining situation in mining would be, thousands of degrees, takes a lot of electricity or burning a lot of coal or whatever to make that, these will operate at room temperature, and they are just as efficient at extracting resources. And we've been using them to do exactly that. So chalcopyrite, the world's most important copper mineral, it freely dissolves in the DESs, and the curves in the middle show the percent copper extracted in some experiments I've run. We extract 100% of the copper. So we're getting complete dissolution at essentially room temperature. And it works on lots of different minerals. So galena, this is one of the main lead minerals. So you might be thinking, lead, that's a metal from the 60s. We don't use lead anymore. They took it out of petrol in the 80s. Why would we have that? I was surprised to learn this, but every electric car, despite having lithium batteries, has a lead battery that runs the electrics in the cab. I thought that was rather strange, but so we still need lots of lead. Galena is the main lead mineral in the world. This graph would seem to show that we don't dissolve lead particularly well. We actually dissolve it amazingly well, but it instantly precipitates out in the DES and forms this white powder. That's actually great, because it means it's separated and we can just scoop the white powder out, and that can go and be turned into metallic lead. It's fairly easy, and there's very green renewable processes to do that. The bonus for this, well, there's a few bonuses. One is that antimony is a byproduct of lead refining at the moment, and we get simultaneous extraction of that antimony, but also simultaneous separation. So the antimony goes into the liquid while the lead precipitates out. So we've got a quick way of separating the two. One of the main problems with lead production is the emissions to the atmosphere of sulfur. We don't have that problem here. This produces no gases. The sulfur precipitates with the lead, but can be easily separated just by putting it in water, because sulfur floats. So this is, potentially an incredibly green, no emission process for refining lead. And it also works on those strange, unusual minerals that sometimes contain the things we want. So on the far side here, we have a mineral called calaverite, which is gold and tellurium. I keep going on about tellurium, sorry. It dissolves that very easily. And this is a mineral that traditionally has been discarded at mines. Even though it contains gold, it's been discarded because it's too hard to process. Well, for deep eutectic solvents, no problem. Here we have a mineral called stannite. This is one that in Cornwall, my colleagues are very excited about as a potential, not just copper, but tin source. And tin is important for solder in our circuits. Again, it's another one that is actually historically quite challenging to process, but deep eutectic solvents, we dissolve it no problem. So we're really excited about deep eutectic solvents. And all the work we're doing is part of, I mentioned it earlier briefly, the circular economy. So the idea is that we are more efficient. We have a better resource management across our entire economy. So not just mining. Mining is where the resources start, but all the way through physical processing, extractive metallurgy, we should be optimizing our production. And then when we're designing products, we should design them so that, one, they don't only use as little amount of metal as possible, but that we can take them apart. Because one of the big problems with recycling at the moment is a lot of things we make, we can't actually take apart properly. You know, you get a lithium battery, it's incredibly hard to recycle because it's glued together in a way that doesn't let it be easily dismantled. So you make it so it can be, so that when you do dismantle it and recycle it, you can feed everything back into the circle. That's the idea behind the circular economy, which is the kind of the broader project I work on. But I think you'd have guessed that I'm just the filthy mining side of it up in that corner. If you'd like to know more about issues surrounding critical minerals, clean energy transition, I'd really heartily recommend the role of critical minerals in the clean energy transition report by the IAE. It's available free online, and it's got some amazing figures, some of which you've seen today, which when I first read it, it was, you know, I couldn't believe some of the things I'd taken for granted and didn't fully understand about metal supply. If you'd like to learn more about what we've been doing at Leicester and, you know, the circular economy and the NICER program in general, we've just had an article featured in Geoscientists that kind of outlines what we as geologists are contributing to it. And, you know, also check out our website if you can find it. I can't remember the address right now, but I'd just like to say thank you to, you know, my funders, which is UKRI, as well as my colleagues, Professor Gowan Jenkins and Dr. Dan Smith in the geology department. And thank you all for having me.
Thank you very much indeed, Phil. That was really fascinating. Can I take any questions? Let me go first to the chat online, because there's one waiting here for us already. So has any work been done to look at when, over the next 100 years, mining suitable asteroids becomes feasible and economically viable?
Yeah, thank you to Colin Jenkins for the question. A lot of people have certainly been thinking about whether you could mine asteroids. Iron nickel asteroids or C3 chondrites have all got quite a lot of metal in them, and that's the thing we're after ultimately. Right now, it's one of those pipe dreams that probably isn't going to happen. And you know, there's been some interesting developments. NASA came up with a microwave technology for processing minerals a few years ago that is prospectively very useful. And you know, spoilers, but we've done a bit of work with the deep eutectic solvents because they are just great at dissolving all metals. So if you put a bit of asteroid in there, it dissolves pretty quickly. But there are such huge barriers to actually achieving that. And you know, when you think about it, why would we? There are a lot of metal deposits on Earth, and it's a lot easier to get to. And there's a whole bunch of economic issues with if you go into space and mine an asteroid and bring back 6 tons of platinum, you've kind of put 50 million South Africans out of a job. So, you know, there are moral issues around it as well. Yeah, so maybe one day, but it's probably a case of when we're actually trying to build things in space rather than bringing it back to Earth.
Thank you very much indeed. Are there any questions in the room? I can bring a microphone to you if you like. Let's try this week so that everyone at home can hear.
Yeah, it was interesting to hear about deep eutectic solvents, which sound like a game changer. How far are they from actual large-scale implementation?
So the technology has existed for a while, but has only really been thought of as commercially viable for the last few years. I have some colleagues in the department who are working with a company called DEScycle to commercialize the project at the moment, and they're building their pilot plant. So that's kind of mid on the scale of, you know, technological readiness. They're sort of halfway, but they're working on recycling mainly. In terms of mining, it's very early days. We're still kind of working out what's possible. But yeah, as I said, we're really excited about it, and it has some real potential. So we're very excited.
Let me come round to take a question from the other side.
I don't think Tom realised today would be such a workout.
A wonderful talk, and thank you very much for that. And but I think tending towards the gloom rather than the cheerfulness. It suggests all sorts of questions about all sorts of things, and we'd be here till next week, I think, discussing them all. But in particular, what's as equivalent amount of work being done on what to do with the 99% of stuff that you dig out of the ground and the big hole that you make there? They seem to be ultimately usable objects. Is there work being done on that?
Yeah, there's a lot of work being done to try and find something that can be done with all of the tailings. There have been several large prizes over the last few years that are awarded to research institutes who are coming up with things you can do. Conceivably, you can make, bricks and stuff out of them if it's the right composition. Some projects in Europe have actually been able to go to a system where they produce zero waste because they're lucky enough that their deposit, the waste product, is a perfect aggregate. So it goes off for building railway lines and houses and things like that. Part of the problem is that these things have a lot of metal in them. And even once we process it, there's still a lot of enrichment in these strange metals in them. And it makes them quite unsuitable for doing a lot of things. You can't make concrete out of it because it rots. You can't make bricks out of it because the metal just rots it. Some really interesting work has started to be done in, can you use tailings to sequester CO2? So can you use your tailings to absorb CO2 out of the atmosphere? So there's some, people are looking into it, but it's an incredibly difficult material to work with. And I will address the other kind of thing you said of a bit on the gloom side. Yes, I have been described as a pessimist a few times in my life. But I think what I would like, if I could say one thing that I'd take away with you, is that this might have been a little bit doom and gloom, but there are a lot of people working really hard to make things better. As I said, we need better mines. Right now, our mines aren't great. They cause problems, but we can do better. And mining companies are trying to do better. And people that research mineral deposits and mining are trying to push that forward. And I think for the people in the room here and the people at home, what I'd like if you came away thinking that the metal you have in your everyday life is a bit more precious than you realized. It took a lot of effort to make it. There's a big cost involved with it. I described the impact of my wife's wedding ring. She will probably be stressing about how much trouble this little thing has caused. So when you're throwing away your old television, don't take it to the dump. Take it to the recycling facility, because the metal that's in it, it was precious. It took a lot of effort to make. If we all sort of do that little bit, then it means it's a little bit less we have to mine. There's a slightly smaller hole. So
thanks very much, Phil. That seems like a lovely place to end, except we have a question in the chat, which I suspect might be controversial. Brian Waters asks, what about minerals from the seabed? Another very hot topic. All the hot topics seem to be to do with mining at the moment. So the seafloor is potentially one of the world's great untapped resources. On the seafloor, you have manganese nodules that form, and these are formed by metals in the water column that precipitate out. They contain not just manganese, but all sorts of critical technology metals. You also have around seamounts, so think around Fiji and Hawaii. You get these manganese crusts that form through a similar mechanism, and there are huge swathes of this stuff. These are some of the biggest potential deposits on Earth. But are they worth it? Because the only way we can mine them basically will destroy the seafloor. It will destroy some of the most biologically diverse places on the planet. And ultimately, it might be a lot of there, but there are a lot simpler and easier to mine manganese deposits up on the surface. So why would we? Very good. Right, I shall come back down to the front of the room. looking around me on the way to see if there are any other questions from the room. But if not, then I'll come to the front and just give you some very quick announcements about upcoming talks in the series. So our next meeting will be in a month's time on the 8th of March. Please bear with me while I just finalize the speaker details for that, and we'll send out the full details as they come in. But that's not the end of the season. We have the annual general meeting and a social event on the 29th of March, and that will be held in the New Walk Museum. So we're trying to hark back to those pre-COVID days and get back to the museum for a bit of a social. That should be a really nice event, so please do support that. And please, we're looking for contributions from our members, little displays or short talks, very informal. So please get in touch if you have anything in mind. And then into April, we have our joint meeting with the parent body. That's on the 3rd of April, when we have a talk from Professor Lynn Frostick on flood risk management. So please join us for that. That's also hosted at the New Walk Museum. And quick comment from Roy.
Let's draw your attention to the bit of this talk. It's about the London project.
Is that right?
So,
Delivered by
the man from Manchester who headed the team.
Dean. Right, thank you very much. I mean, I've just been asked to remind you, notice the fact that the parent body is hosting a talk. It sounds as though from Dean Lomax, who headed up the Rutland Sea Dragon dig, along with Mark Evans, one of our own. And so to hear updates on that, that's at the parent body in a couple of weeks' time, I hear. So please look that up as well. Right, I think I've given all the announcements I wanted to. So it just remains to thank Phil once again for a really excellent talk. Thank you very much indeed, Phil.